Okay, so continue with what we had yesterday. I showed you one example about a shaft under various loads everywhere. So first we will have balance of forces, balance of moments to find out the loads everywhere. Then we will figure out the shearing force from the very left. By walking toward the end, we will figure out how the shearing force distributes. Then we will take integral. Then we have the moments. Once we have the moments, we can use the equation 32m over pi t cubed to calculate the normal stress. If we have torque, then we can use the equation 16t over pi d cubed to compute the shearing stress. So based on the example yesterday, supposedly we should be able to figure out anywhere inside a shaft what the stresses are applying to somewhere inside the shaft. So let's say this particular point is the location with the largest normal stress, like some point from yesterday's example. Then we can draw something like this. It's being pulled from left to right, or being compressed left to right. So in this particular case, I want to use the tensile stress, so meaning pulling, and then we have shearing from top, bottom, left, right edges. What can we do if we have a figure like this? So usually, in most of the shaft problems, at the end we have a drawing like this, okay? So please remember how it looks like, because most likely in your exam it looks like this. Due to bending and twisting, it's usually, the shaft it can be easily bended, and it's either being pulled from the left and right or being compressed from the left and right? And you can twist the shaft. That's why you usually have shearing stresses. Next, we would like to talk about is Mohr circle. So what's happening is you need to figure out a different orientation of your observation. And if you know about Mohr circle, if you can change the direction of your observation, it's possible for you to find another orientation where the stress is even larger. So in this current orientation, we have normal stress and shearing stress, but if we change how we observe the same point, the stress condition on each surface is different. So we just want to change how we observe it, and eventually we will find a new orientation, and we will see so-called the principal coordinate, principal axis. On the principal axis, we have the largest normal stress. So if we only use the original normal stress to design our material, that is actually not the largest stress being applied to the material. Along a different direction, the stress is even larger. So like what we wanted to do at the beginning, we need to find the worst loading condition. Principal stress direction is the worst loading condition. Okay, so let's learn or remind ourselves how we can study Mohr's circle. If you already know, it's just an easy review. If you forget, then it's a good opportunity for you to learn Mohr's circle again. Now, whenever you are in the stress diagram like this, or a free body diagram like this, you need to pick up a point on the edge somewhere and choose it as a starting point. When you do that, you will draw another figure on the right, and the coordinates will be different. The coordinates is a normal stress and shearing stress coordinate, a sigma and tau coordinate. That's a coordinate keep tracking on the analysis you did, or the stress condition you observed on different positions surrounding that point. Okay? So, starting from here, let's say, okay, it's like a initial position with 0 degree. And we found there is a normal stress in the magnitude of sigma A, and there's a shearing stress in the magnitude of tau A. So it's easy to recognize the direction or positive and negative of sigma. Whenever it's pointing outward, we say it's tensile and we define as a positive. So that must be a positive sigma A. That's why we have a positive value sigma A right here. But for the tau, you can define on your own. You have to say, if it's clockwise, it's positive, or counterclockwise is positive. You have to define it properly. And what I usually like to do is to follow the right-hand rule. So I like the right-hand rule to be positive. So the counterclockwise, I define it as positive. I do see different references use a different orientation. It's fine, as long as you specify it. So if you choose clockwise as positive, then the point will be at the bottom, right? Either way. Now I say counterclockwise positive, so I know from my analysis, I realize there is a counterclockwise shearing stress in the magnitude of tau A, so maybe some value like this right here. So I pick a point, I specify a point. So that's the loading condition at this particular direction. Next, I move the position of my observation. I move by 90 degrees, and then I try to observe the exact same point, but along different direction. So over here on the top, there's no normal stress. However, there is a clockwise tau A. So if I specify a point B in this drawing, it's gonna be somewhere here, because there's no normal stress, 0 here, and negative tau A. That's your point B. If I continue to move forward, I move to the point C, I realize the loading condition is exactly the same. It seems exactly the same as A. So it seems like I'm getting back to point A again. And if I keep on moving downward up to here, I will move up to the same point, B here. So it's like if you make 90 degrees of movement in the free body diagram, you are moving 180 degrees in the Mohr circle coordinate. So please remember, whatever angle you move inside the free body diagram, you are going to move double the degree, double the angle in the Mohr circle coordinate. So the reason why we would like to call it Mohr circle, we realize it's actually a circle. Okay, and if you want to find the center of the Mohr circle, you can connect point A and point B. And it seems like if you move around the entire element. You can move from A and move up to C, then you already make one round of the Mohr circle. So this circle basically is indicating the stress condition at any angle, everywhere. If this is the case, then you realize if you move to some position right here, the normal stress is even larger than the original coordinate. That's what I meant. If you observe the same material in a different orientation, you could be having a greater stress. If you have greater stress, then that probably is a better coordinate for design. Because in design, we want to say the worst loading condition cannot be greater than how strong I am. Okay, so if one day someone punched me in my face, so probably that force pointing to my nose is the strongest. If I observe the stress distribution of my face, and I didn't observe along this nose direction, I observed in a different orientation, I realized, hey, there's no stress. I thought I'm strong enough. However, when I change the way I analyze the stress, I realize, okay, here is where I get the most impact. So I need to figure out along the direction with the most impact, how much stress I'm carrying, and am I strong enough? That's the idea. Now, when we try to figure out the exact location of this, the largest stress, we call this the first principle stress. We realize we need to rotate clockwise by 2 theta, some angle 2 theta. So in the free body diagram, we will be rotating the exactly same coordinate by theta, because the rotation right here is gonna be double of the rotation on the left. So if we call this angle 2 theta, then in this coordinate we rotate by theta. So what does it mean? What happened? Why does the square rotates? There's no square. It's just a point. Okay, so it's just like originally we're observing this point straight, but we now tilt our head a little bit by the angle of theta, and then we change the way we observe it. Like I said earlier, whenever we draw a square, it's just to indicate, to exaggerate how large the point is, but in fact it's just a point. Okay, so don't be confused by that square. Oh, who rotated the square? There's no rotation. In fact, it's just us. We just bend our head and then try to visualize the point in a different coordinate. And we draw a square in parallel with the new coordinate just for us to have better understanding of what happened. Now, in this orientation, sorry, I call this point D. This is the direction where we rotate the coordinate by theta, and over here exactly rotating by 2 theta. We found, we end up with a point at the very right edge of the Mohr circle. At that particular position, we only have normal stress, no shear. So when we rotate our coordinate, we realize along this direction, there's no shear stress, only normal stress. That's why we call this principal stress coordinate, principal axis. And along this direction, if you from here and rotate by 90 degrees, and over here you will be rotating by 180 degrees, you reach another edge of the Mohr circle at the very left edge of the Mohr circle. It turns out in this particular case, it's just one example. In this particular case, it's a negative value. So in this illustration, it turns out this one is negative. It doesn't mean it's always like that. It's just the way I define the problem and I draw how large the vectors are. It turns out the second principal stress ends up on the left-hand side of the coordinate. It's a negative value. That means there is compression along that second principal stress direction. Okay? So that completes the free body diagram along this principal axis. And you can tell there's no shearing stress. Now, if we rotate the principal stress coordinate from here, and if in the free Mohr circle, if we rotate the coordinate, rotates the observation point by 90 degrees, we will end up with somewhere somewhere we have the largest shearing stress. So we usually call it a tau max. At point F is where we have the tau max. So when we rotate by 90 degrees in this Mohr circle, that means we need to do some rotation here again. Earlier we were straight, and we bend our head by theta. Now we're gonna rotate back by 45 degrees, and it turns out it's a new way of observing the same point. But along this direction, we realize we have the most palpable largest shearing stress of this element. So over here, our shear are the largest. So if there's a material that is afraid of shearing stress, most likely when it's gonna break along the shearing plane, it's gonna break along some coordinate along this direction or this direction. Because this is the orientation where we have the largest shearing force. Okay, so in the field of materials or manufacturing, many times they try to observe how a material fail. And they usually try to figure out, okay, along which orientation the material cracks. And in many times, it's cracking along the shearing plane. Okay, so please be aware that when we are starting at the position with the maximum shearing stress, it doesn't mean there is no normal stress. There is still some amount of normal stress. That's why there are still some normal stress here and there. Okay, so that's Mohr's circle. Now we want to know how to compute it. Okay, I always think you don't need to memorize the equations because you have a diagram. You have a figure right here. From geometry, you can easily compute the coordinate of any position. But if you are someone who likes to memorize equations, or you want to know what is a quickest way or most systematical way to compute this, usually what I do is I try to figure out what's the radius. Okay, so the radius could be computed by this small triangle. Here, this is what you're looking for. The radius is exactly the same magnitude as the maximum shear stress. So this is actually trying to compute the radius. But what I did was I chose a triangle right here, and you can easily tell the height is gonna be tau A, right? And that is wrong. Is that wrong? No, it's not wrong. Okay. From this point to this point is sigma A. but you only need a half of it, right? That's why this distance is half of the sigma A. So you take the square root of half of sigma A and take a square of half of sigma A and take a square of tau A and sum them up, take the square root. That's why the radius could be computed like that. Then how do you compute the first principal stress and the second principal stress? It's quite easy. You can use this distance, which is half of sigma A, plus the radius, or minus the radius. So here is adding the radius minus the radius. That's how you can get the first principal stress or the second. Okay, so if you compute the radius, you can easily get the first and second principal stresses. Okay? Any questions? If you have learned this, this is so super easy for you. Now, sometimes we don't like to compute the sorry, it's not we don't want to compute. Sometimes we have even more general case where we have both normal stress and shear stress at the B position. In this particular case, that means the B point is not on top of the tau axis. In that case, the equations could be more complex. However, is nothing new. Okay, same idea. You compute the radius, so you need the square of this distance and the square of this guy. How do you get this guy? This is basically a half from the projection of B and projection of A. So this particular distance. So this distance basically is sigma A minus sigma B, right? Because sigma B is a negative value. So this minus this, you will get the width from the projection of A to projection of B. And take a half of it, then you have this distance. That's why you have something like this. Square plus tau square, take a square root, then you have the radius. Similar to what I did earlier, how do you get first principal stress and the second one? First, you figure out the coordinate of this guy. So this is like at the middle of sigma A and sigma B. The middle point basically is like an average value of both. So how do you take average? You sum them up and divide it by 2. Then you have, this is basically sigma F. And you add the radius or minus the radius. From here, add the radius or minus the radius. You can have your first or second principal stresses. Okay, should be very easy for you. It's just that if one day I ask you to derive this without reviewing, you may forget how to do it. But it's actually quite easy to understand. So I want to remind you how those can be calculated, because later on in most of our design models, you need to compute the principal stresses. Now, there's one special model I want you to understand, because this is also related to our design model later on. Okay? This is the Moore circle for tensile test. So what does tensile test mean? Tensile test means you have a material and then you pull it until you break it, right? There's no any other external forces, no other forces. So the force diagram looks like this all the time. At the beginning, why did I draw it horizontally? Because to match how I actually if I draw it up and down, it's You still have, you end up with a drawing like that. It's just, I want this to be A, I want this to be A. So it doesn't matter. It's like you are observing the tensile test by tilting your head. Anyway, for tensile test, at the beginning, there's no stress. Once you apply the force, you start to pull, based on the analysis of our Mohr circle, your Mohr circle looks like this. So initially, the circle is so small. There's no circle. As you apply greater and greater loads, the circle starts to expand, but it's always having this shape. It's lying on this horizontal, the center is lying on this horizontal plane. It's just that this value is increasing, the circle is getting bigger and bigger. Okay, that's the Mohr circle for tensile test. Okay? So in that case, you can realize, even for tensile test, there is still shearing stress somewhere. Where? By the 45 degree. When you pull, like if this is the workpiece for tensile test, you're pulling like this, by rotating the coordinate, by 45 degree, that's where you have the shearing plane. That's where you have the maximum shear. Okay? So sometimes if you observe the tensile test, and sometimes it breaks along the shearing plane. Okay? So there's one important parameter, which is the maximum shear. The tau max in tensile test is a half of sigma A, right? Because of the radius. That number is important. That number is important. Tau max equals to sigma A over 2. Okay? That's important in future models. Keep that in mind. Okay? For more complex problems, actually here is a 3D. In fact, in general, this is not in the test. Just for you to know, if you have a material that's having what's happened when you are dealing with 3D model, but plane stress problem. We're still working on a plane. However, what's happening is there's no stress along the third direction. So it's like a stress in the plane. In that case, what truly happened is you can try to study the Mohr circle between first and second coordinate, second and third coordinate, and third and the first coordinate. If you do that, in fact, we have 3 Mohr circles. Each Mohr circle represents a working plane, either 1, 2, 2, 3, or 3, 1, right? And it happens that the stress along the third direction is 0, so in fact, you have circles like these. And usually the Mohr circle that we work on is the one between first and second. So the largest one is the Mohr circle that we usually draw. We don't even draw the Mohr circle along the other 2 planes. However, you keep that in mind, there actually exists stress analysis along different directions. It's only because they are smaller. The stress between the stress on 2, 3 plane and stress on 3, 1 planes are smaller than the one on 1, 2 plane. So sometimes we don't care. Okay, but keep that in mind. There is a drawing like this that says something. Okay, you can actually make drawings of the stress conditions on different planes in a diagram. Okay, but each one of them represent the stress behavior in different planes. Okay? Just for you to know, when you see something like this, you won't be confused. I think that's it for this particular point. And the other one, back to, oh, there's a problem. Oh, no, that's not the file. I should download this one, I think. We should work on get back to the problem we had, the example problem we had yesterday. Okay, so back to the same problem. Yesterday we figured out these are the, let me see how to full screen it. This, that's fine. Okay, so yesterday we already figured out at somewhere over here there's that's the position with the largest normal stress, and we have the same shearing stress everywhere. So that's the low condition of that particular point, worst loading point. Now we can figure out, okay, somewhere on the at the skin at the parameter of at the edge of the cylinder, somewhere over there we have the stress diagram like that, and the magnitudes are basically the values you got from earlier analysis. So if you want to draw a Mohr circle, it's gonna be something like this, exactly like how I did it, but this time because the shearing stress goes down on the right edge. So at the beginning, this is a negative value for point A. Rotate by 90 degrees, then I rotate 180 degrees. I have counterclockwise shear, so I have positive value over there. So you draw the Mohr circle. The next question is to ask you what's the magnitude of principal stresses and also the maximum shear stress. So exactly the same thing that I did in the previous slide. I compute the radius. I found the center position, and then center position plus the radius, center position minus the radius. I got the magnitude of first principal stress and the actually the exact value of the second principal stress. It's a negative value. It's close to zero. Okay, but it's still there. Now, what do you do next? No more. That's exactly what you need to do right after the stress analysis. So get back to the problem again. I want you to do a homework and do everything like what I did here. Okay, this is your homework. So you have everything you need. However, I'm gonna ask you to do something so that you will experience this problem quite differently. Okay? So, for the homework, exact same problem. So here's our shaft, right? And we have two bearings. The other one here, right? And we have two pulleys, larger ones. Okay, so this was the problem. But now I want you to do something. I want you to choose this edge as your y coordinate. Okay? And I want you to reverse and have your x coordinate here. So if that's the case, let me use the right-hand rule to figure out where is your z, x, y, and z, right? Z goes into the board. Right. So everything goes the same, but your coordinate system changed. And if you do that, the way you compute balance of moment will be almost the same. It's just that the coordinate is different. But the way you draw the shear diagram and the moment diagram will be completely reversed, right? Because you are now standing on the right, and then your x0 is here, and then your x goes this way, and your y goes up. That means every value right here will be different. Every equation right here will be different. So it's a very easy trick for the teacher to give a problem. You have all the answers. It's just that the way you observe a problem is following a different coordinate. So you can follow exactly what I did, but using the new coordinate, and you have all the figures to check whether you made something right or wrong. And if I made something wrong, you can help me and tell me, hey, something's wrong here. I hope there's no mistakes in mine. Okay? So do exactly what I did. Try to solve the exact same problem using a different coordinate. Don't worry, I won't give a complex problem like this in the exam, because our exam only lasts for 1 hour. So it will be much simpler. But when you go home, I want you to experience the whole thing. First, compute the reaction forces, determine the shear and moment diagrams, figure out what's the position with the worst loading condition. So that will be somewhere here, exactly here, but different coordinates, because your 0 is right here. Your 0 is right here, okay? At the very right edge. Now draw the Mohr circle, and then figure out the principal stresses. Supposedly, they will be the same. Okay, that's your homework. So please give back in 1 week, and everything written by hand. So if you have a helper on your homework, at least you did some effort on copying. Right? When I was a graduate student, tell you the truth, my math teacher gave us probably around 10 homework problems every week. In some number, like 6 or 7 homework problems every week. So I still remember every day I'm doing my homework until 2 a.m. every day. And I have a roommate. Actually, he lives upstairs. I usually go to his room and do my homework. He's also Taiwanese. I am someone who's trying to get PhD and become a professor. He is just someone trying to get a degree. He wants to just pass everything, get a degree, and then come back home, become a boss. Yeah, because his family has a company, and he just needs that degree. So later on, when he does business, he can say, "Hey, I'm a master's student. I have a master's degree," something like that. So he doesn't work as hard as me, and the reason why I like to do my homework in his room is because you always playing Xbox, and his Xbox playing is my background music. So I was doing math homework, he's playing Xbox. So I usually finish the homework until 2 a.m. and he will use 1 hour to copy my homework. And that hour from 2 to 3 is my time to play Xbox. Yeah, that was my master student's years. First year. I was taking a lot of courses, a lot of homework. So the senior student always tell us, take more when you are more junior. So later on, when you work on your thesis, you don't need to take courses anymore. So I took 4 courses, and in my lab, I still need to work. So my lab is like a 5th course. So it's like every week, I need to handle those 5 important things. And later on, in the 2nd semester of my master degree, I became a TA. So my job as a TA is to teach AutoCAD. I'm the lecturer. I'm not the TA grading. I'm not the grading guy. I'm the lecturer. So can you imagine when you are in the 2nd semester of your 1st year of your master, you are a teacher? The student will call you, hey, Professor Paul. I'm not professor, I'm just a TA. It was something like that. So when I was in USA, I stayed in New Jersey for 7 years. I taught computer graphics for 6 years. So it was very scary when I was a student, Taiwanese, teaching English. Everyone downstairs is like American and people from different countries. They ask me questions. I need to figure out what they are talking about. So yeah, it's okay to copy, but make sure you learn. No, I shouldn't say that. It's not okay to copy, but I won't catch you copy, right? I won't know. But if you copy, at least learn from your hand, right? Because it's important. In the first exam, it's gonna be something like this. It's gonna be a different shaft problem. Maybe it's not a pulley anymore, it's a gear or something like that. So you won't know how the problem look like. So you need to get familiar with this. So please, it's very important. And I can tell you, this one is the hardest one. The first exam actually is the hardest. Because later on, when we talk about the design equations, we have equations, plug in, then you get numbers. Later on, it's gonna be easier. But this one, you need to have long derivations, especially here. I will ask you to draw a diagram in your exam sheet. So it takes a lot of time to have a drawing like this in the exam within 1 hour. Okay, so please practice. That's it for today. We have the, where is it? Attendance stuff? Attendance, where is it?
桌面，我有放桌面。
哦，
也有网站上也有。
It's okay.
云端上有，桌面也有。那个9月13。
This one?
哎，上。
This one?
Yes, that's right.
Okay. So if you have not done attendance, please do it. It's important to do it this time because some of you were not here. So it's good for you to take 1 point more advanced than the others, right? Okay, that's it. If you have questions, you can come here. Otherwise, please remember to do your homework. A week later, we will collect it, the handwritten ones. Okay, bye.